Socrates. He believed that the earth and everything around it was made up of three things: earth, air, water, and fire. Only now do we know that that is incorrect, and it was in fact another Greek philosopher, Democritus, who was correct. He believed that all things were made up of these tiny little particles he called something that sounds like atoms. Either way, we now know that that is correct, and that the world is made up of, and all the universe is made up of tiny, tiny little particles that we can't even comprehend, called atoms. And each atom makes up specific elements. Now, as I said before, everything that we know is made up of elements. And that's pretty incredible, because we only know of slightly more than 100 elements, and yet there are millions of different molecules made up by compounds of elements in the universe. So that's pretty cool. What do you guys think has the highest percent of the Earth's atmosphere? That's right. It is oxygen, making up about 49% of the crust and atmosphere. Now, another thing that is pretty important to us is our bodies, because that's kind of how we live. What do you guys think is the most abundant element in the human body? Yes, also oxygen is the most abundant in the human body, with about 65%. What do you guys think is the second? Well, about to throw a curveball at you. It is actually carbon. Makes up about 18%. And it's not just like pure carbon and pure oxygen in the body. It's like they form different molecules. Anyway, thank you. Okay, now we are back to naming elements again. And now, like, you guys may be wondering, how did we get the names for these elements? There's so many of them. How do we name them? That's crazy that, like, people come up with this. Well, to start off, some elements people have known for about as long as humanity existed, such as, like, gold and iron and silver, mostly pure metals that don't really form chemical bonds with other elements. And it's kind of interesting because we call iron, obviously, because that's how it's spelled in English. But you may notice that on the periodic table of elements, it is actually Fe, not even close to iron. Like, the word iron doesn't even have an F or an E in it. And that is because in ancient Latin, the name for iron was actually ferrum, like this. And that's why we call iron, that's why iron's abbreviation is Fe. And another element they also knew about was gold. And instead of having a G on the periodic table, we have an A and a U. And that is because their pronunciation, what they called gold, was aurum. There's something similar to that pronunciation. And that's kind of how they came up with that. And I don't really know, no one knows specifically why we have these specific elements named after those abbreviations, but that's kind of how it is, mostly because Rome was just such a dominant force. But also, you guys may be wondering, but hey, there's tons of other names for elements, like, what about Einsteinium? And that is because a lot of times they name elements after extremely famous scientists, like Albert Einstein, or Dmitri Mendeleev, who was the creator of the periodic table, had an element named after him, Mendelevium. But it's not just people and places. Like, obviously we have aluminum's symbol is just Al for aluminum, and that's kind of how it is. And carbon and oxygen, all of them just have their names, what we call it. But new elements have been found recently, and they've started naming them after places. Like, one of the newest elements found is Nope, they're not an M. Sorry, that's my bad. That was a little blunder. Nihonium. And that is because it was discovered by a Japanese team of scientists, and in Japan, they pronounce what's it called? The country of Japan, in Japanese, the name of the country is Nihon. And for some reason, ium is they just kind of always add ium to the end of elements now, like einsteinium, mendelevium, nihonium. It's just kind of how it is. And there you have it. That is how elements are named. Okay, now we have discussed what elements are and their electron configurations and everything, and now we're going to talk about the periodic table, which is how they are organized. And they were organized by, and the periodic table was created by a Russian scientist named Dmitry Mendeleev. And basically at the time, everyone kind of had their own way of modeling, of putting the elements into order, but none of it really made sense to him. And so what he did is he found that he along with a couple of other scientists found that every atom has a certain, or every element has a certain number of protons, electrons, and neutrons that make up the atom. And what he did is he organized it by the atomic number, which is the number of protons in an atom. And so say for hydrogen is number 1 on the periodic table, and it is just H and then a 1 above it. And then it also has an atomic mass of 1, but that doesn't really matter for what we're doing right now. So basically what he did is he organized it in this way, and so it goes like this, and the periodic table is shaped something like, kind of like this. Not great drawing, obviously, except this is kind of what it is shaped like, and then here is helium. And so basically, in the periodic table, there are rows and columns. And right here we have a row. And really the ones we want to know about is the first row, which is alkali metals, because all these rows, or all the columns, excuse my speech, all the columns share certain properties with each other. So outside of hydrogen, which doesn't really go along with these, the first column, the alkali metals, are extremely reactive metals. If the pure substance is exposed to air, there's usually combustion. And then there are the alkaline earth metals, which are also extremely reactive. And then we have the transition metals right here, just in this general area is the transition metals, and they're basically the metals we know, like iron, gold, silver, all those, and they conduct electricity. They can form bonds, but a lot of the times they're found in their pure form. And then, sorry, this is a terrible drawing, but around here we have a staircase, basically, and underneath the staircase is what we call the metalloids, which kind of have the properties of metals, but at the same time have properties of nonmetals, and that's why they're called metalloids. And then over here we have our nonmetals, which are usually in gaseous states. And in the second to last column we have the halogens, which are also extremely reactive because they want to gain one more electron. And then over here we have the noble gases, which are very unreactive. And the reason why the alkali metals and the alkaline earth metals and the halogens are all really reactive is because they all have very extreme electron shells. So over here, as we all know, every atom wants at least 8 electrons in their outer shell, or for helium and hydrogen 2. And so over here, they're very close to getting 8 electrons. They just have to lose one, so they combust and react with other elements to lose the extra electron to form the outer shell. And over here they want to gain one. And so the closer they are to 8 electrons, the more reactive they are. And then the noble gases are really the only ones that don't form compounds. And I think there you have it. That is the periodic table of elements.
Starts 4.5 to 4.7. The structure of the atom, the introduction to the modern concept of atomic structure, and isotopes. What is the plum pudding model? The plum pudding model is a model of the atomic structure. proposed by J.J. Thomson in the late 19th century. Thomson had discovered that atoms were composite objects made of pieces with positive and negative charge, and that the negatively charged electrons within the atom were very small compared to the entire atom. Now to talk about the parts of an atom. An atom contains three particles: electrons, protons, and neutrons. Electrons are negatively charged particles found orbiting the nucleus of the atom. The nucleus of the atom contains the protons and the neutrons. The protons contain positive, so protons and neutrons are found in the nucleus of the atom, and electrons orbit around the nucleus. And protons and neutrons are...
So here we see a beam of particles being shot through tinfoil to see if they'll separate and scatter to detect alpha particles. Rutherford's experiment was very different from what he anticipated, and the particles passed straight through the foil and did not deflect.
Here we see the mass and charge of the electrons. The electron, with a mass of 9.11 to the 10 to the negative 31st power, and has a negative 1 charge. The proton has a mass of 1.67 to the 10 to the negative 27th power, and has a positive charge. The neutron does not have a charge and has a mass equal to the protons with 1.67 to the times 10 to the negative 27th. In 4.6, we start seeing a chemist asking this important question. If all atoms are composed of these same components, why do different atoms have different chemical properties? And they were trying to figure out this answer, but we know today that the answer is because of the different amounts of neutrons and protons in an atom, they make different properties of elements. They are the glue of atoms, and they make up all the chemical properties. And this leads us to isotopes. Isotopes are atoms of the same element. Okay, here we have the atomic structure of lithium with 3 protons, 3 neutrons, and 3 electrons. 2 electrons in the first shell and 1 electron on the second shell. So when lithium gets a 4th yellow ball or neutron, it's called an isotope. And that is... stop it.
Okay, so now here's an example. Pretend we'll have chromium 58. Now we want to know how many protons, neutrons, and electrons are in here. Looking at the periodic table, we know that chromium 58 has 24 protons. And the protons and electrons have to be equal for this to cancel out. So we have 24 electrons. We do not count the electrons when trying to find the number of neutrons for chromium 58. So we'll take 58 minus the 24 protons, and we get 34 neutrons. 34 neutrons.
Bang.
Okay, so let's pretend we're trying to find an isotope for iron. We're given the information that iron has 27 neutrons. So for this, we look at the periodic table and find that iron has 26 protons, and with that, 26 electrons. Now we add the 27 neutrons plus the 26 protons to figure out what the isotope is, and we get 53. So this is iron 53, guys. So here's a question for you. Protons and what have almost equal mass? The answer is neutrons. Okay, question number 2. Are you done? What particles in the atom are responsible for the chemical properties of the atom? It is protons. Okay. Example 3. Let's say we have carbon 16. And we want to find the number of protons, the number of electrons, and the number of neutrons. We look at the periodic table and find that carbon has 6 protons. And with that means it has 6 electrons. So now we have the number of protons and the isotope number. So we'll subtract 16 minus 6 and get 10. So we found out that carbon 16 has 10 neutrons. Okay, it's Caden here. In 4.7, we're talking about isotopes. And now we're gonna find the formula for interpreting symbols for isotopes. The formula is A minus Z equals the number of electrons. So, for example, let's say we have carbon 12, which is written like this. A is the 12, and Z is the 6. 12 minus 6 equals 6, and that's how you find the number of neutrons. So pretend we have sodium 23. So here we have the formula A, Z, and X. The A, or the 23, represents the mass number, or the number of protons and neutrons added together. The Z here, or the 11 for this, so here we have an isotope symbol. So we have sodium 23 here, and the formula is AZX. The A, or the 23, is the mass number, or the number of protons and neutrons. The Z, or the 11, is the atomic number, or number of protons. So to find the number of neutrons, we subtract 23 minus 11, which gives us 12. So we have 12 neutrons. Okay, so now we can tell that sodium 23 has 11 protons, and when it's balanced it also has 11 electrons. And since we subtracted these two numbers, we get 12 neutrons, and that's how you write it in the isotope formula or symbol. Okay, so to summarize 4.5 to 4.7 notes, which covered the structure of the atom, the introduction to the modern concept of the atomic structure and isotopes. We have, what is the plum pudding model and who created it? The plum pudding model is a model of the atomic structure proposed by J.J. Thomson in the late 19th century. Thomson had discovered that atoms are composite objects and made of pieces with positive and negative charges, and that the negatively charged electrons within the atom were very small compared to the entire atom. What is a nuclear atom? It is an atom with a dense center with a positive charge around its tiny electrons. What is the nucleus? It is the positively charged central core of an atom. A proton is a particle with a positive charge in the nucleus, and the electron is the negatively charged particle that orbits around the nucleus. What is an isotope? It is atoms with the same number of protons, but with a different number of neutrons. What number next to the isotopes does it signify? It indicates the isotope's mass and number, or the mass number. How can you tell isotopes apart? Isotopes can be told apart by their mass numbers. What is the atomic number? The atomic number of protons in the nucleus. What is the mass number? And that is the sum of the protons and neutrons in the nucleus that are added together. And that's a summary of my section.
All right, so we're going to demonstrate how a cation goes from cation to a neutral element to an anion. So we have Chase over here, who is being the model of an aluminum element who's actually a cation of aluminum with 3 extra protons. So what I'm going to do is he has 3 extra protons, I have 6 electrons, and I'll show how when I give him extra electrons, he's going to turn to a neutral element and into an anion. So first, we're going to throw an electron at him, and by doing that, it cancels out both the electron and the extra proton. And I'm going to throw another, and then he's going to be a neutral element now since he doesn't have any extra protons. And now I'm going to give him some electrons. Now he is negatively charged into an anion. And to be more specific, it is an anion of a -3 charge.
Alright, so we are going to balance these charges out, and in order to do that, we need to first neutralize them so that both the charges of each element equal 0. So to do that, we need them to cancel each other out. So with the aluminum, we can see right up here that it has a positive charge of 3. And over here, the chlorine has a negative charge of 1. And so, in order to cancel these charges out, we need to add 3 chlorine to this 1 aluminum. So, it's going to look like this. And this is because since we are having 3 of these negatively charged chlorine, it's going to cancel out these 3 positive charges of a single aluminum. Alright, so let's move on to something a little trickier, which is beryllium with a +2 charge and nitrogen with a -3 charge. And so to do this, like before, we need to neutralize them so that both charges equal 0. And to do that, we are going to add 6 beryllium and 3 beryllium and 2 nitrogen. This way, both the charges equal a +6 and a -6, which, when combined, equals 0. Alright, so I'm going to draw diagrams of the states of matter for an element. So for solids, the molecules are usually compacted much closer than any other state of matter. That's how they become solid, is because all the molecules are tightly put together and compact into this one object. Now, for liquids, it's a little different. The molecules aren't as compact and not really touching each other like a solid. Instead, they're a little spread out compared to that, but they're more spread out to freely move instead of just be compacted and squished together. Now, for gases, the molecules are all over the place and they're bouncing everywhere. So, for gases, completely spread out, they have no connection to each other at all. Liquids are a little bit put together. That's how they kind of flow smoothly and together. And solids are compacted into one figure, one object. So now going on with what I said about gases, I stated that the atoms in gases were spread apart and they like to bounce around quickly, and that they were separate. This is true for some gases like argon. They're completely separate. The atoms and the molecules just, they don't have a pair or anything. But for other gases, there are molecules called diatomic molecules. And just as the name suggests, these molecules for the gases are paired up with each other. And as a pair, they do the same thing as the molecules of an argon gas would do. They just bounce around, but just in a pair. And some examples of these would be oxygen, nitrogen gas, oxygen gas and nitrogen gas, and helium gas. Hydrogen gas. So let's talk about allotropes. So allotropes are this really cool thing with elements. It's basically a single element that has different forms to it. So one very common example of this is carbon. So carbon has 3 distinct forms to it, and that is diamond, graphite, and another one called Buckminster fullerene. And so basically right here is the Lewis structure of both the diamond form and graphite form of carbon. And as you can see for the diamond form, you can see all the carbon atoms are connected with covalent bonds. And since they're only connected with covalent bonds, it makes them real strong and they hold together real tight. For graphite though, you can see that they are also connected with covalent bonds for each carbon atom, but along with that, they are stacked in layers. And the thing about these layers is that they have weak binding forces that connect them, which doesn't really keep them together as well as the structure of a diamond. Hello, this is Australian Nick with compounds that contain ions, or in this case, ionic compounds. And so, as you can see, we have a lovely example, very simple. Okay, my accent's gone because I can't hold that forever. But this is an example of sodium chloride. And so, for ionic compounds, there are 3 specific rules that need to be followed. So one rule is that it must have, the compound must be between a nonmetal and a metal. And another rule because of that is that they must have both positive and negative ions. And as you can see, we can see that sodium chloride is following these rules because it has both a metal that is sodium and a nonmetal that is chloride. And it follows both the positive and negative charge rule because chloride has a charge of -1 and sodium has a charge of +1. And so the last rule, probably the most important rule in order to make it a compound, is that the compound needs to end up with a net charge of 0. And this picture, I mean, you can't really tell for sure, but just from what it looks like, you can see that from this one side, that the charges cancel each other out, making them have a net charge of 0. Okay, so I'm going to give a quick example on how to make an ionic compound by balancing out the charges to equal a net charge of 0. So for this ionic compound, I'm going to be using lithium and nitrogen. And so for lithium, we know that it has a charge of +1. And for nitrogen, we know that it has a charge of -3. And so basically for this, what we have to do is make it so that this number and this number equal 0. And so for this, we just use simple algebra, and we basically use 3 lithium in order to get a +3 charge on the lithium, and then we leave nitrogen the same so that that can cancel out with the +3 charge of the lithium. And this ionic compound will give us a net charge of 0.